Okay, so thermodynamics. Often I've taught this second semester. I've never put it in conjunction with thermochem. So this is just a reminder, some things that you probably, depending on what you've been doing recently, you may or may not remember. So conservation of energy, the energy is just not created. We know the first law of thermodynamics is delta equals Q plus W. Remember, Q has to do with heat and W is work. Your change of enthalpy is equal to delta E plus P delta V. Q equals MCAT from the calorimetry world, and that we could find delta H using our formations with our appendix data. And so that's just a reminder, some stuff related to this that we would have already done. So spontaneity, in the new current terms, we're going to say thermodynamically favorable, and non-spontaneous, we're going to say tough for thermodynamically unfavorable. That is the new verbiage that AP and College Board would like us to use. So spontaneity, a reaction will go without help, and this tends to be exothermic reactions tend to be spontaneous, and that is a prediction. Non-spontaneous, a reaction will need assistance for it to happen. Endothermic reactions tend to be non-spontaneous or tough, thermodynamically unfavorable. So notice I did put this note about reactions can be spontaneous in the forward directions and then non-spontaneous in the reverse direction. So that's something to pay attention to in which direction you are asked. So entropy is represented by the letter S. It has units of joules per mole Kelvin is usually how we will see it. The larger your entropy value, the larger your degree of randomness or disorder. So basically everything in the universe is favoring towards having a greater entropy because it's easier. So think about how it's easier to keep a dirty room than it is to keep a clean room. So a positive S is a more increase in disorder. If we have that increase in disorder, we're likely to be spontaneous or thermodynamically favorable. If we are decreasing disorder, we're likely to be thermodynamically unfavorable. Entropy is a state function, means independent of the path to find it. This typically is like a multiple choice kind of question you can see on an exam. We can find delta S naught at standard conditions using the same appendix data we used to find delta H. Sometimes you'll see this equation for finding delta S at a constant temperature. I'd worry more about that in the engineering world and not necessarily on the AP exam. Now the second law of thermo says the entropy of the universe is always increasing. So it's the second law. And the third law of thermo says entropy of a pure crystal is zero at absolute zero. So the first law had to do with conservation of energy, and then these other two laws have to do with entropy. So there is a molecular interpretation of entropy. This might help you with like a multiple choice kind of question. I do want you to realize that you could predict entropy without having the values by looking at states of matter. So entropy of a gas is going to be higher than the entropy of a liquid, which is higher than the entropy of a solid. If the states of matter are the same, then we're going to look at the number of moles of reactants and products. If we have more moles, then it's going to have a higher entropy value. There are also entropy changes with molecular motions, not motionals. You get a translational, vibrational, or rotational. So translational, you're moving in one direction. Vibrational, you're like a tuning fork. And rotational, spin like a top. Again, this is for like a higher level course. I just wanted to let you know that that would be the case. Now, we did do Gibbs free energy last year. Gibbs free energy will tell you for sure if a reaction will occur or not. Delta H is a prediction. Entropy is a prediction. Gibbs free energy tells you for sure. So its units are in kilojoules per mole. Okay. And so if it is a negative G, it is going to be thermodynamically favorable. If delta G is 0, we're at equilibrium. And if it is a positive G, that means it's non-spontaneous in the forward direction or it's thermodynamically unfavorable. We can find delta G using our appendix data, just like we did for delta H and delta S. That is not as likely though. Okay. Delta G is 0, just like delta H is 0 for elements in their normal state. Most likely how we deal with delta G is this equation here. And if you recall, I tagged on last year the change of joules to kilojoules, knowing entropies in joules per mole Kelvin, to just go ahead and stick that conversion onto your T delta S. That would ensure that your units always agree. Okay, so that's what that statement has to do with. So delta G equals delta H minus T delta S. Your temperature is always in Kelvin. And so that means we can find delta G at any temperature. It does not have to be at 25 degrees C. So if we're given H and S, we can find G, and that could be at different temperatures. Now this chart I would memorize. This is very likely multiple choice kind of questions that you may see. And so looking at the signs of delta H and delta S, you can tell is something spontaneous along with your delta G. Now, notice it does say things about low temperature and high temperature. Usually in the question statement, it will say low temperature or high temperature. It's not going to give you like 300 K, and you're supposed to know if that's low or high. Okay, free energy and equilibrium. Most of the time, we're not going to be exactly at standard conditions. So these equations are the ones I would suggest. And so the more common one we're going to use is the second one that's highlighted. So this first one is at non-standard conditions. We're going to find our delta G naught at standard conditions. R is our gas law constant, which is in this form, 8.314. Temperature would be in Kelvin. A natural log of Q. Q and K are found the same way. Just a reminder, K is products over reactants. Okay, so if I have A aqueous plus 2B aqueous yields 3E solid. We do not include solids and liquids. We do include aqueous. That'd be 1 over A times B squared. So that's that quick and dirty KEQ review. And there is some stuff posted about how to do that as well. So Q is when you're not at equilibrium. And so that means if we're not sure, we're going to use Q. Okay. And so for a system at equilibrium, we're going to have a different equation. Okay, so if we're at equilibrium, that means delta G is 0 and Q is equal to K. Then we're going to use this equation. I would say this equation is what you'll see much more likely on the FRQ. So if there's one you have to remember, that's the one I would remember. Okay, so it's the same idea. You can find delta G naught equals negative RT ln of K. Now R is your gas law constant, T is your temperature in Kelvin, and then K is your equilibrium constant. One thing to note, the units of R are in joules. So I would throw in a conversion of converting that into kilojoules before you solve for either of these equations. Sometimes AP likes for you to relate equations together. And so notice we have several equations that start with delta G. So we could set these two equal to each other. So we could say delta H minus T delta S equals negative RT ln of K. So this is where like AP likes to check your understanding of how things relate. Now, if negative G, then your log of or natural log of K is positive. That means your equilibrium constant is greater than 1. If you have a positive G, that means your log or natural log of K is negative. K is less than 1. If delta G naught is 0, that means K is 1. Okay, so I have this practice problem here. And so you're given a bunch of information. You're given this reaction, and you're told delta G at 298 K for a reaction mixture that contains 1 atmosphere of N2, 3 atmospheres of H2, 0.5 atmospheres of NH3. You're given H and S. So I could find delta G naught easily using this part. I probably will need to write my equilibrium constant or my Q because I'm not sure. So Q is going to be equal to NH3 squared all over N2 times H2 cubed. Just a reminder, I did tell you to use P's if they're in gases. So actually the better way to write this one would be Q equals P NH3 squared over P N2 times pH2 cubed. Okay, so that's, again, I would use the P's here. That's the more correct form. AP used to not worry as much, now they do. So I'm actually going to plug those values in. That gives me my Q. I'm going to use this equation that I mentioned with that conversion to get me to my kilojoules. And then I'm going to plug everything into this equation of delta G equals delta G naught plus RT ln of Q. Again, we have to use the one with the Q. And notice my gas law constant, I'm converting to kilojoules. So it's just a bunch of plug and chug. Okay, last one is kind of a similar problem. You're given a reaction. If you notice, we have a bunch of solids, so our equilibrium constant would only include carbon dioxide. That's why it looks like this. Okay, and so we could use a different version of that rearranged equation. You're given the delta G, taking care of that conversion. Here's your gas law constant, temperature. This style problem tends to be a little harder in the calculator. And lastly, free energy and work. For a spontaneous process at constant temperature and pressure, delta G equals negative work max. This is for the Brown and LeMay book, so don't worry about that. Okay, and don't worry about the brick. Okay, so that is thermo in a nutshell.